Welcome back to Circles, everyone. To finish our discussion of this topic, I wanted to cover a few fun theorems that'll lead us to our last couple of proofs for this section. We left off talking about inscribed angles, so let's talk a little bit about a polygon inscribed in a circle has the same property as an inscribed angle, which is to say, all of the vertices of its angles lie on the circle. For instance, here are a couple of inscribed triangles. Both and are inscribed in this circle. Let's call it circle P. But knowing what we already know about inscribed angles, we can already say that angles D and B have to be congruent, because they intercept the same arc. And as we've already seen, no matter where we were to put D between A and C, its measure would be the same as B. One of those strange facts about inscribed angles on circles. The theorems we're going to look at today all have a bit of this trickery about them. For instance, consider this situation. Let's say we have circle C with diameter xy. And let's say that xy is one side of an inscribed triangle. I'll just arbitrarily draw the rest of that triangle in here. Now we have triangle XYZ inscribed in circle C, but we can even be a little bit more specific than that. This triangle is actually inscribed in a semicircle, in exactly half of circle C. And the topic of our first theorem is whether or not we can find something special about this kind of triangle. So the claim the theorem is making is that it doesn't matter what kind of triangle we inscribe in a semicircle in this way. That is to say, where I put Z on the circumference of circle C, that triangle will always be a right triangle. Seems to be a somewhat remarkable claim, but a proof of this theorem is pretty simple. We only have to make use of a theorem that we've already proven. If xy is a diameter of circle C, then we also know that xcy is a central angle of the circle. And not just any central angle. Obviously, this divides the circle into two semicircles, which means that its measure must be, and let's not forget one of the best circle theorems, just making use of this theorem allows us to say that angle Z has got to be a right angle. Try writing out the formal proof yourself, but you'll see that no matter where we put Z on circle C, we end up with a right triangle. But let's say, instead of talking about an inscribed triangle, we talked about an inscribed quadrilateral. Quadrilateral ABCD certainly matches our definition for an inscribed polygon, but other than that, there doesn't really seem to be anything particularly special about it. Let's say it's inscribed in circle P. Well, before we prove a theorem about this, let me give you a little tip that will make you very popular at parties. When you're talking about inscribed quadrilaterals, we often call them cyclic quadrilaterals. Pull that out at your next gathering, I'm sure that everybody will be fawning over you. But what can we say about cyclic quadrilaterals? Supposedly, if you're willing to believe everything I tell you, this theorem says it's the case that the opposite angles within a cyclic quadrilateral happen to be supplementary. So maybe this is not so average a quadrilateral after all. But let's think about a way to prove this. The first thing that jumps into my mind is that all four angles of the cyclic quadrilateral are inscribed angles in circle P. We've already used an important theorem about inscribed angles today, so maybe we can use it again. Let's create a central angle, in this case APC. Of course, there are two angles APC, what looks like the obtuse angle, and then a reflex angle. We know it has to be the case that we'll use that superscript r to mean the reflexive angle APC. So the measure of angle APC plus the measure of its reflex, of course, have to give us 360 degrees. This is how we defined reflex angles. An angle and its reflex are going to form the entire angular measure of a circle. But let's start considering these inscribed angles in relation to the central angles that we've just formed. How do the measures of this inscribed angle and this central angle relate to each other? Well, we've just used this theorem already. We know exactly how a central angle and an inscribed angle that intercept the same arc relate to each other. Then, of course, we should ask the same question about this other angle pair of an inscribed angle and a central angle, where the central angle we're talking about here happens to be the reflex of angle APC. If we use one of our favorite circle theorems here, we should be able to answer this question. And of course, noting that angle ADC and angle ABC are opposite angles in this cyclic quadrilateral, this question mark had better have something to do with the way we stated Theorem 2 above. So if we begin with an inscribed quadrilateral, a cyclic quadrilateral, pardon me, and we draw in two radii, AP and PC, we should be able to follow these steps to prove Theorem 2. Why don't you give it a try? The last theorem I want to talk about actually doesn't have anything to do with inscribed angles at all. There's one other type of angle that we should consider with regard to circles. We'll call it a circumscribed angle. I'll do my best to sketch out two tangents from point X to circle Q. When we talk about circumscribed angles, this angle X is the angle we're talking about. It's just an angle whose sides are tangent to the circle. We actually already know a heck of a lot about tangents from external points to circles, and we can actually use that information to prove an important theorem about the measure of circumscribed angles. First, we should notice that this circumscribed angle intercepts an arc YZ. If we want to know what the measure of arc YZ is, we just need to find the central angle that intercepts it. This last theorem involving circumscribed angles tells us this in this particular case: that if we know the measure of arc YZ, then that measure plus the measure of the circumscribed angle must be 180. Another way to state this so that we can use our familiar word supplementary is just to substitute out the measure of arc YZ for the measure of its central angle, and leads us to be able to state this theorem. Which is to say that we should be able to add the measure of angle X and the measure of angle Q and get 180 degrees. And proving this will be our last proof having to do with circles. So let's think about how to make this proof happen. Well, to the original circle Q, we had circumscribed angle X that's tangent to circle Q at Z and Y. That's our definition of a circumscribed angle. Then we added radii Y, Q, and ZQ so we could create angle Q. As usual, I think it makes a lot of sense to think about triangles here. But even before we create triangles, there are a couple of things we can say. We know that the two radii we created have to be congruent to each other, because all radii of the same circle are congruent. But we also know, as we've proved, that these two tangent segments have to be congruent, since tangent segments from the same external point to a circle are always congruent. You might notice that this actually creates a kite, and there's a theorem about kites having to do with the opposite angles along this long axis. But let's go back to the fundamentals and see if we can prove this. As is our habit, let's create a couple of triangles. Remember, of course, this statement is where we're trying to land. Well, it's pretty easy to prove these two triangles congruent to each other. We already have two pairs of congruent sides, and the good old reflexive theorem tells us that XQ has got to be congruent to itself. Side-side-side congruence has never been easier. But once we have side-side-side congruence, how is that going to help us get to this statement? Well, CPCTC certainly leads us to understand that these two statements have to be true. In fact, they're already marked for us in the diagram. We have congruent angles here, and we have congruent angles here. There's one more fundamental piece of information that we need to know in order to complete this proof. We've already proved this to be true, but we know that tangents to a circle are perpendicular to the radius that shares the point of tangency. So these two triangles that we've created aren't just any triangles, they're right triangles. As a result of this, we can say that the acute angles in either of these triangles, which are the four angles that we discussed in this step, well, each pair of them within the respective triangles have to be complementary. We know this about right triangles. So these two acute angles have to be complementary. And likewise, this sum has to be true. Think about a substitution that we could do here that would allow us to construct the larger angle x and the larger angle yqz. Here's an idea. This is just the angle addition postulate. We can do the same thing for yqz. We already have two 90-degree angle measures here. Perhaps we can use those to add to 180. I'm going to leave the last couple of steps to this for you to work out formally on your own. And once you've proven these theorems, I think you'll find that the algebraic problems to which they give rise are pretty easy to solve. Try out the proofs to these three theorems, and then we'll move on and make use of them. Have a great day, everybody.